A buffer overflow is an anomaly in programming where when writing to a buffer, the data goes past the buffer's allocated size and overwrites any memory after it. This is a major security flaw as it can allow attackers to exploit the workings of a system to access information that otherwise should not be accessed or even execute arbitrary code. In this video we'll be looking at heap overflows. These are buffer overflow attacks that target data stored in the heap rather than the stack, meaning it focuses dynamically allocated memory. Modern compilers typically attempt to patch potential buffer overflow vulnerabilities. One way they can do this is by moving all the buffers to the end of the stack to try to prevent overflow attacks from modifying instructions. There are many other countermeasures taken automatically to help developers against these attacks. This does not apply to heap overflows because the memory is dynamically allocated. Compilers do give some warnings, such as the gets method, which the C documentation actually recommends should never be used, as it can very easily cause buffer overflows. To demonstrate the very basics of a heap overflow, I have written a simple program that has two dynamically allocated buffers. Each buffer is 16 bytes, so it should store 15 characters plus a null terminator. If we copy some strings into each of those buffers and run the program, we can see that it works as expected. Buffer 1 contains 15 characters, as does buffer 2. But now we can store more data in buffer 1 than expected, overflowing the buffer. We now see that the data copied into buffer 1 has overwritten data in buffer 2. Note that although buffer 1 is only 16 bytes, we had to write 32 bytes into buffer 1 in order to reach the start of buffer 2. This is because malloc pads data with 16 bytes so that the free method can work. Interestingly, we haven't had to disable memory randomization or any flags in the compiler to run this. We've just seen that heap overflow can be used to overwrite data in memory. As a simple scenario, I've written a program that has a login feature. The user is presented a main menu where they can either reload the main menu or go to the login page. At the login page, if the user enters the correct password, the program will say the password is correct and exit. Otherwise, it will ask the user to enter the password again. Though the password is easy to find because it is stored in the code, imagine there was some more advanced process happening to check the password, such as communicating with a server database. Looking at the source code, we can see that the menu option is retrieved using the gets method, where it is stored into our buffer. The program determines whether the user is logged in using a Boolean value dynamically allocated after the selected option buffer. By overflowing the selected option buffer and storing any value greater than 0 into the dynamically allocated bytes for the Boolean, that Boolean is now regarded as true by the program. The program now exits and thinks we're logged in without ever having to enter a password. As a third example of heap overflow, we will be demonstrating a popular example of changing the execution of code in a program. In this demo program, the user enters their name as an argument, and the program then gives them a message back. A function pointer is dynamically stored in memory, which is then executed to display this message. The code is meant to call the default function method, but using a buffer overflow, we can change this to execute the method not default function. This is a bit more complex as it requires analyzing where in the heap the pointer is stored and where in the stack the method is stored. Using gdb-pedder, we can disassemble main and see that the execution of the function is at +102 call rdx. If we create a breakpoint at this line and run the code again, and then use vmmap to look at the memory layout of the program, we can analyze the heap and find the memory address of the data we entered as an argument, and we can also find the memory address of the function being called. We can show that it is actually a function by disassembling the dereferenced pointer. We can see there are 32 bytes between the start of the buffer and the start of the function pointer, so we need to overflow by 32 bytes. We can find the address of not default function method by using disassemble and getting the address of the first line. Now if we use a simple Python script to write 32 characters and then the memory address of the not default function method, we see that the program runs a different function from what it is meant to.